is atomic size, usually on a relative basis, not an absolute basis, and electronegativity, both properties of atoms with which you've already heard quite a bit. We'll start with a review of atomic size considerations, believing that you certainly heard about atomic sizes in Chemistry 2045, and presumably, in addition to recognizing the principal size trends for atoms in the periodic system, heard some explanation of these size trends. So, this is the stuff we revisit. More detailed explanation is, of course, available in the notes. That's your job to read that stuff. I hope you do. So, as we said, this is our main theme. These are properties of atoms that we have to be familiar with to get at this. Main size trends for A family atoms. I trust you heard in Chemistry 2045 that size trends, in many cases, can't even be established for transition metals, or in certain cases, post-transition metal atoms. Because when you get valence electrons, which are d in character, you get a lot of aberrations in size trends. So the comments which we offer are about A family atoms. Main trends as you go from top to bottom inside an A family. From period to period for the atoms inside that family, you usually observe a significant expansion in size. Sodium atom, a lot bigger than lithium atom. Potassium atom, a lot bigger than sodium atom. And if we were going to take hydrogen and helium and cut and repaste the symbols for those atoms, I presume you have recognized that on the basis of single valence electron, hydrogen, of course it has only one electron, which is S, you could put it on top of lithium on this basis. On the basis of two 1s electrons, the total electron and therefore the valence electron configuration for helium. Where would you put helium? Well, based on its properties, you'd certainly put it on top of neon. But what about electron configuration? Top of beryllium. Aren't the 2A family members all with an S2 valence pair? Isn't that like helium? But back to the trends. As we go across a period, just for A family atoms, like period number 2 or period number 3, the general size observation is that atoms get progressively smaller as you go from atom to atom. I know of no exceptions to this. Usually with a slight shrink. Certainly a slight shrink compared to the large change in size that you see for atoms in the same family, A family atoms in the same family. This top to bottom size increase, or bottom to top shrink. The upshot of which is we expect beryllium not to be a whole lot smaller than lithium, but smaller. Boron perhaps not to be a whole lot smaller than beryllium, but smaller. But by the time you go from lithium to beryllium, you've looked at the relative sizes of 8 atoms. So on this basis, you can expect a neon atom to be a lot smaller than a lithium atom. Now, I trust you recognize that this trend is in some ways unusual, at least when you first think about it, because lithium, how many electrons total? 3. How many nuclear protons? 3. Neon, 10 and 10. Here's this neon particle with many more protons and many more electrons. A lot more particles, but nevertheless a lot smaller. So something's got to be happening to the ability of nuclear charge to attract electron density toward the nucleus as you go left to right. It's got to be increasing. Next, which we've already mentioned, but it's part and parcel of this consideration, lithium versus sodium. Size difference, sodium a lot bigger. Particle composition. Sodium 11 protons total, 11 electrons total for the neutral atom. Lithium 3 and 3. Well, if you're going to believe that the attraction force exerted by valence electrons is directly proportional to atomic number, you're going to believe that sodium will be larger or smaller than lithium, more easy or more difficult to ionize than lithium. What are you going to believe? If you're going to believe that nuclear attraction for valence electrons is directly proportional to proton count, total nuclear charge, would you expect sodium to be smaller or larger than lithium? Notice when we went from lithium to neon and experienced as you go from atom to atom and adding additional proton in the nucleus and an additional electron, 3 electrons, 3 protons in the nucleus lithium, 10 electrons, 10 protons in the nucleus neon. Which one is smaller? Neon. A good deal smaller. Which one is harder to ionize? Neon. A hell of a lot harder to ionize. In fact, from an absolute basis, neon and helium are the most difficult atoms in the periodic system to ionize. This accounts for why helium as yet has not been found to react with anything. Of late there was some, I believe, account of a possible reaction for neon, but I don't know if that as yet has been verified. Well, if you're going to extend this trend to sodium, would you not expect sodium to be smaller than lithium? Would you not expect sodium to be more difficult to ionize than lithium? Yes and yes, and you'd be wrong and wrong. So something's got to happen as we go left to right across a period. That's a heck of a lot different from what we observe as we go top to bottom inside a family. Did you think about that in 2045? And what we just said accounts for the fact that Z effective not directly proportional to Z. For in family A atoms. What's Z effective? What's that mean? If you talked about these size trends in 2045, then you heard about Z effective. Z total, that's just total proton count, atomic number. What's Z effective? Z effective is the term applied to the actual nuclear attraction which a particular electron that's part of an atomic electron configuration experiences. And of course, what electrons are we talking about? Or, pardon me, I should say, what electrons are we principally concerned with? The valence electrons, because those are the electrons which account for the reactivity of an atom. Well, got to be a big difference Certainly sodium versus lithium. 2s1, 3s1. But lithium 3 protons in the nucleus, sodium 11. A hell of a lot more protons. Over 3 times as many. But sodium is still bigger and easier to ionize. Now, as it relates to this size trend inside a family for A atoms, take a look at radial probability graph A. That's on page 2310 in the notes. I provided a gee whiz sketch of this graph, but what you see in the notes is indeed a copy of this graph as it is meant to look. For these graphs, the horizontal axis, call it the x-axis if you want, is a measurement of distance from nucleus. Here's the nucleus. Here's the nucleus, okay? And as we go on the vertical axis, call it the y-axis if you want, that's a measure of radial probability. Did you hear this term, radial probability, in 2045? Radial probability. Imagine that you can stand at the center of an atom. You can stand in its nucleus. Pick an atom with a whole bunch of electrons. Any atom with a fairly substantial Z value fits that bill. You're standing at the nucleus. If we take an atom to be a spherical entity, then as you stand at the nucleus, you're going to look toward the exterior surface of the atom, I don't care what direction, and see for an A family atom, 1A, for a 1A family atom. You're going to try to see the outermost electron. Now, what do we know about electrons? They're interesting and mysterious creatures, aren't they? They don't behave exclusively like particles. They have this wave character. The upshot of which is you can never pinpoint an atomic electron. You can never know exactly where it's at. All you can do is have a probability of finding it at a given distance from the nucleus. And that position from the nucleus where you most often find it is called most probable distance. That's this MPD thing that I've got abbreviated in these graphs. How do you think MPD relates to atomic size? Let's imagine that this graph that we have here is for a potassium atom. Based on the electron configuration for a potassium atom, we know that it's got 1s electrons and 2s electrons and 3s electrons and a single 4s electron. So it's also got 2p electrons and 3p electrons. Has it got any 4p electrons? Potassium? I'm just poking at you to see what you remember about electron configurations. Now, how about potassium? Has it got any 3d electrons? Yeah. I heard a vote for yes. What atom in the periodic system is the first atom to have a d electron in its configuration? This you should know. The first transition metal atom. That's number 21, scandium. So our vote for the presence of d electrons in the configuration for potassium is incorrect. The total configuration for potassium is made up of s-type electrons and p-type electrons. That's it. Okay? So we're standing in this nucleus of potassium. And we know that its valence electron, its 4s electron, accounts for its chemistry, its chemical behavior. So as we stand at this nucleus, we want to look to the surface of the potassium atom to see where most often this 4s electron resides. That's called MPD, most probable distance from the nucleus. How do you think most probable distance from the nucleus for the 4s electron of potassium relates to the size of potassium? If you look in a table of atomic radii, and you see an atomic radius tabulated for potassium in picometers or angstroms or nanometers, whatever the units that's used. What does this radius value mean? How does that relate to MPD for potassium 4s electron? Did you hear this in 2045? I mean, you need to know what this stuff means on a practical basis. At least I think you do if you want to understand it. It's the same thing. Doesn't that seem reasonable to you? If the highest n-value electron for potassium atom is 4s, and we find out where this 4s electron is most of the time, its most probable distance from the nucleus, then that is the distance you are in fact observing when you, at the same time, observe the size of a potassium atom. So MPD is certainly a measure of atomic size, at least for these atoms which have valence s electrons. Now, this graph can also be viewed as a graph which to an extent compares the size of hydrogen with a 1s electron, lithium 2s electron, sodium 3s electron, these are of course valence electrons, and potassium 4s electrons. Well, that's not really true. This graph is really representing where you will see, say again for the potassium atom, its 4s electron relative to its 3s electrons, relative to its 2s electrons, relative to its 1s electrons. But it does, nevertheless, provide a parallel to the size trend, which we've recognized for A family atoms. For atoms in the same family, like these 1A atoms. How would this graph, if we take this graph to represent the s electron radial probability distribution for potassium, would this graph look exactly the same if we make it for calcium? Would this graph look exactly the same if we make it for scandium? Would this graph look exactly the same if we make it for gallium? Well, if the graph doesn't look exactly the same, then how is the graph different? In this case, if we look at this graph for calcium versus potassium, given that we're imagining this graph to represent this s electron radial probability distribution for potassium. How does the graph change if we look at it for calcium? We're looking at the same electrons, given that calcium, like potassium, also has 1s, 2s, 3s, and in the case of calcium, a 4s pair, valence pair. How does this graph differ if we look at it for calcium? If I draw this picture again, if I say this is for potassium, and I want to draw this picture for calcium, how's the graph going to look different? General shape, would it be different? No. Well, how's it going to differ for calcium? The difference will be in these MPD positions. How? For calcium, will the MPDs be shorter or longer? We're looking at the same kind of electrons, except that when we go from potassium to calcium, we're looking at an atom which now has one more proton in the nucleus. Do you think it's fair to conclude that the calcium atom has its S electron radial probability distribution compared to this for potassium, showing that all the MPDs are somewhat shorter for calcium? It's the same kind of electrons. So you have the same core electrons, the electrons which are inside, in this case, the 4s electrons. You think these MPDs would be a little bit closer to the nucleus for calcium? What if we look at this graph for zinc? Zinc's got all these electrons too. But now we're looking at atoms got 30 protons in the nucleus. Are these MPDs going to be even closer to the nucleus for zinc than for calcium? What do you think? In 2045, did you hear about these terms which may sound mysterious? We've already talked about one of them called Z-effective. I'm talking about the other terms that you will hear about if you're going to talk about establishing rationale for size trends of atoms, besides Z-effective. We've looked at a graphic representation of this stuff. This is radial probability graphs. Shielding, did you hear about shielding? Penetration, you hear about penetration? Penetration is a measure of the ability of a particular electron to get through electrons that are closer to the nucleus than the electron in question. Well, if this electron we're talking about cannot effectively penetrate through these inside electrons, then the electron we're talking about is effectively shielded. On the other hand, if this outlying electron, like a 4s electron for K, is effective at penetrating through these inside electrons, simultaneously that means it's not effectively shielded. And these all relate to atomic size. Did you hear about these terms in 2045? Then we're talking about these questions over here. We already talked about the difference between Z and Z effective. Effective shielding by core electrons. Now for potassium and calcium, you think it's fair to conclude that these highest N value electrons, single 4s electron for potassium and 2 4s electrons for calcium, are more or less shielded to the same extent? Because the inside electrons, all the same. 1s2, 2s2, 2p6, 3s2, 3p6. There they are. That's the argon core. Did you hear the term core electrons in 2045? We talking about that? No, we just talked about the core electrons for K, Ca, and all those other atoms that you come across in period number 4. Those are the electrons which primarily account for shielding. Do you think electrons in the same orbital shield each other? How about electrons in the same energy level? I'm just curious if you heard about any of this stuff. Well, let's back up just a little bit. and talk about the two simplest atoms on a relative size basis. The two simplest atoms of the periodic system, hydrogen and helium. If a hydrogen atom floated in here, and a helium atom floated in here, and you had eyes which had super microscopic character, and you could see this hydrogen atom and this helium atom. Here we would imagine the hydrogen atom will be orange, and the helium atom will be blue. That kind of familiar for folks at this here place? Which one is larger? The orange sphere or the blue sphere? The orange sphere is the hydrogen atom. The blue sphere is the helium atom. We not only have the magnificent ability to see these atoms, since we were able to see them, we painted them. Slop, 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 orange on the hydrogen atom, slip, slop, 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 blue on the helium atom. They're going to be the same size? Well, if they're not the same size, then they're different sizes. Which one is bigger? Hydrogen's bigger. Now, are there any core electrons for these atoms? Huh? Did you ever hear about energy level 0? Is there any such a thing? Or energy level 1/2? Is there such a thing? No. For convenience and simplicity, we identify the first energy level with the simplest quantum number, 1. You remember that quantum numbers are strictly positive integers? Principal quantum number n is strictly a collection of positive integers. No fractions, no negative values, and 0 is not part of the game. Okay? 1, 2, 3, 4. Well, hydrogen 1s electron, helium a 1s pair. These electrons don't have any core electrons. Now, what's the difference, hydrogen, helium? Well, hydrogen, 1 electron, 1 proton, that's it. So you got a Coulombic attraction force proportional to a charge of +1 acting on this particle with a charge of -1. The trouble is this damn thing isn't just a particle. It's this wave thing. So even for this simplest atom, the hydrogen atom, you can never know exactly where that hydrogen atom electron is. But most of the time you can know where it is. That's given by the size of the hydrogen atom. It's called the Bohr radius. 0.529 angstrom. Did you hear about that in 2045? The Bohr radius? Well, I guess maybe I should quit talking about 2045 because I keep finding out you didn't hear much about anything in there. It was, of course, so damned easy you didn't have to pay attention to what went on in class. You just bubbled in the right circles on the multiple choice tests and took it from there. I made an A. I didn't learn anything, but I made an A. That's terrible. Well, forget that. Okay. Helium. 2 protons in the nucleus, 2 electrons. So when we get to helium, we have something, electrically speaking, that we don't have for the hydrogen atom. It's called repulsion. Because these 2 electrons, which live in the same orbital, 1s orbital specifically for helium, they have the same electric charge. Both minus, at least that's the way we've labeled it. And these things repel each other. Now, does electron repulsion for the atoms which are part of the same configuration, for the electrons that are part of the configuration of a particular atom, does repulsion among and between these electrons, which are part of the configuration for a given atom, does that tend to increase or decrease atomic size? Huh? If you got a balloon, something with a flexible skin, and you start pumping a bunch of electrons into that balloon, is that going to cause the balloon to get smaller? Hell no. These things don't like each other charge-wise. They repel each other. That tends to expand, doesn't it? So, if you think about it, given that helium has got repulsion between electrons, whereas hydrogen has none such, because it's only got one electron, you can realize that if this repulsion effect exerted between the electrons, the two electrons for helium, is significant, helium could be larger than hydrogen. But the other side of the coin is, for each of these helium electrons, you've got a Z effective which is proportional to 2 protons. Whereas clearly for hydrogen, Z effective and Z are 1. And it's the only atom for which Z and Z effective are the same thing. That's it. Because you got no repulsion effects and you got no core electrons. So what counts more? The added nuclear attraction for valence electrons, highest lying electrons, when you go from hydrogen to helium, or the repulsion effect between the electrons? Well, the only way to find out answers to stuff like this is to go to the laboratory and make measurements, make observations. And after we make these observations in a reliable fashion, then we can cook up stories to explain these observations. That's these fancy theories that you hear in chemistry class. So what counts more? You already told me you all know that helium is smaller than hydrogen, and that's correct. So is it the added nuclear attraction mean more? Or the repulsion mean more?
Nuclear attraction.
Nuclear attraction's got to mean more. If helium's smaller than hydrogen. Okay? Now then, what property of an atom would you measure if you wanted to know about Z effective? Well, size for sure. But is there another property of an atom you'd wish to measure, wish to know about? If you're trying to get a handle on Z effective, what property of an atom would you be concerned with? I'm listening. You're curious about how strongly an electron is held within the overall electron configuration for the atom. In the case of helium, you're curious how strongly either of its 1s electrons is held compared to the 1s electron of hydrogen. What property of these atoms are you going to look for, measure, observe? Electronegativity.
Ionization energy.
Ah, yes. Ionization energy. You can't measure electronegativities directly. Ionization energy is what you would observe. Now, what we find is that the ionization energy for helium is almost but not quite twice the ionization energy for hydrogen. Almost but not quite twice. The data's in the notes. What does that suggest to you? You remember what Coulomb's law looks like? Written as a proportionality, that's Coulomb's law. I'm sure you've seen this. What I'm curious about is, what's this thing tell you? I mean, if you look at this and the only thing it says to you is something symbolized as small letter f is proportional to something called Q1 times Q2 divided by d squared. If you don't know what these terms mean, this is nothing but an algebra puzzle. Doesn't mean anything. What's it mean? Well, hydrogen, 1 times 1 over d squared. What's this d? What is it? What distance? I know it's distance. What distance? What is it? It's MPD. For the case of hydrogen, it's the size of the hydrogen atom. Pardon me, not the size, but the radius. The distance between the electron and this charge that's attracting it. And that charge that's attracting it is the proton in the nucleus. So it's the separation between the nucleus and the electron at its MPD. Well, tell me, what do we got up here for helium? We're talking about a given electron and how strongly it's attracted by its nucleus compared to the attraction exerted on the 1s electron for hydrogen. Hydrogen 1 times 1 divided by the hydrogen radius squared. Helium. An electron's got a charge of 1. We're not going to pay attention to signs. You know, for protons, electrons, it's a positive force. For electrons and electrons, it's a negative force. Repulsion. That's what the signs mean. What's Q2? Is it 2? Is it Z effective? It's this. What's D? It's the helium radius, quantity squared. Okay? Now, have you not already told me that helium is smaller than hydrogen? Helium is smaller than hydrogen. What impact does that have on the magnitude of F for helium compared to hydrogen? If helium is smaller than hydrogen. Makes the F value larger, doesn't it? Okay? So, this thing is suggesting that helium might be more than twice as difficult to ionize as hydrogen if Z effective for helium is 2 and Z effective for hydrogen is the same as Z, 1. For hydrogen can't be anything but. And helium smaller than hydrogen. If Z effective for helium is 2, given that D is shorter for helium, how would the ionization energy, first ionization energy for helium, compare to the ionization energy for hydrogen? Certainly larger, but by what factor? If Z effective for helium is 2, because it's got 2 protons in the nucleus and there's no core electrons, right? If Z effective is 2, given that helium is observed to be smaller than hydrogen, how would the first ionization energy of helium compare to that for hydrogen? For hydrogen, let's see, IE. Let me look it up. I want to write this down since we're talking about this. 1311. Let's just say about 1300. Of course, this is the ionization energy to ionize a mole of hydrogen atoms. If we divide this by Avogadro's number, you'll get the ionization energy for a single hydrogen atom. Okay? IE1 for helium, because helium has got two ionization energies. Compared to this number. How would the first ionization energy for helium compare to this number if Z effective for helium is 2, given that helium is smaller than hydrogen? Clearly larger, but I want a more specific response than that.
More than double.
More than double. Isn't 2 times 1 twice as big as 1 times 1? That's not hard. And we know that helium is smaller. Okay so far? That guarantees if Z effective for helium is 2, the first ionization energy for helium has got to be more than twice this number. Nothing fancy about the arithmetic. Of course, you've got to let this thing talk to you so it tells you what it means. Now, the first ionization energy for helium is, in fact, about 2,400 kilojoules per mole. What's that tell us? That's one of the neatest and, in fact, and oftentimes most difficult part of science. You observe data. We got data. What the hell does the data mean? I mean, we're never going to understand nature if we don't know how to interpret these data. We've got to know what the data means. What's this mean?
Z effective for hydrogen is greater than Z effective for helium.
Oh, no. Remember, we made the decision that IE1 for helium is more than twice this number if Z effective for helium is 2, because you got 2 protons in the nucleus. We know helium is smaller. So if Z effective is 2 for helium, that guarantees that first ionization energy for helium has got to be more than twice this number. Because it would be exactly twice this number if hydrogen and helium were the same size. Right? 2 times 1 is twice 1 times 1. There's nothing fancy about the arithmetic. But the data tell us this is a good deal larger than this, but this is not twice this. Specifically, there's a line diagram for a 1s orbital. And with these arrows, I have now exhibited, I've diagrammed the electron configuration for helium, haven't I? I mean, this is stuff you did in 2045. I want you to put it to use. You got 2 electrons living in the same orbital. And these electrons have the same charge. And since they have the same charge, they repel each other. The question is, do these 2 electrons, which live in the same orbital, therefore got to live in the same energy level, do they exert any shielding effect on each other? Do they, to a certain extent, prevent each other from feeling this full +2 charge in the nucleus? Is helium more than twice as difficult to ionize as hydrogen? More than twice as difficult to ionize as hydrogen? No. It's not even twice as difficult. So what's that tell us about these electrons? Do they or do they not have a shielding effect on each other? They do! Good. We let the data talk to us. If they didn't shield each other, given that helium is smaller than hydrogen, then Z effective for helium would be 2, and it would be more than twice as difficult to ionize helium as it is hydrogen. That's not the case. So now we know This shielding business gets even more complicated because we've just found out that electrons in the same orbital can shield each other. Not nearly as greatly as core electrons, inside electrons. Well, if electrons in the same orbital can shield each other, then it's a good bet that electrons in the same energy level will shield each other, because electrons in the same orbital are in the same energy level. We're trying to let this stuff talk to us. This is just part of, I'm just going over part of the stuff that you have to think about in order to try to rationalize this damn difficult problem. As things presently stand, with all the wonderful calculations that are being done, supported by these marvelous computers, which can grind bushel baskets of data in the twinkling of an eye, we still have no theory which can explain exactly the size of an atom, and guess what? We're never going to have that theory. Not if the Heisenberg uncertainty principle is correct. Never. It's fun. I like it. Electron beats smart man. Ha ha ha. Now, more on this. Take a look at graph B. Graph B I've drawn. My graph B picture, I'm sure, is better than my graph A picture because the graph B picture is simpler. To an extent, this graph B relates to what we're talking about with hydrogen and helium. Why so? Because graph B is showing an overlay of the radial probability functions for a 2p versus a 2s electron, right? So we're talking about electrons in the same energy level. You know, like helium, 1s electrons are clearly in the same energy level. Hell, they're in the same orbital. Beryllium versus boron, which is smaller? We've already observed a trend, which is really established by helium being smaller than hydrogen. So as you go across period 2, size-wise, you see a small, at least in most cases, but steady shrink as you go from lithium to beryllium on down to neon. And by the time you get to neon, you got an atom that's a lot smaller than the atom you started with, lithium. Same for the period 3 atoms. Argon, a lot smaller and a hell of a lot more difficult to ionize than sodium. Beryllium versus boron. Well, boron's the right side atom, so boron is smaller than beryllium. Okay? Now let's talk about ionization energy. Because so far, we've only talked about properties of s electrons. Right? S electrons versus other s electrons. Now let's extend this to s versus p electrons, so that we can get a handle on how these different kinds of electrons. What are the 4 different kinds of electrons we've learned about? SPDF. We haven't yet needed any other labels. What would be the next label if we needed more electrons to make a configuration for an atom?
G.
You'll find out that we'll need G electrons when we get to atom number 121. We haven't got there yet, but we're getting close. There's an old periodic table. The latest version of a periodic table that I could find is the one that's included in your notes, which I believe shows the existence of atom up to Z118. Take a look. What's in the notes? The Z118 is the highest Z value we got in this table. Table's in the front of the book. Is that it? Z118? I don't know what its name is, and I don't give a damn what its name is. It strikes me strange when scientists start quibbling about things like, what should we name this atom? I don't give a damn about stuff like that. What counts is what we do, not who we are. I mean, Einstein pointed that out on more than one occasion. Back to this graph. Boron is smaller. Now, which atom is more difficult to ionize? We're now getting at property differences between p-type electrons versus s-type electrons. Well, if the general size trend as you go across a period is that atoms get progressively smaller, then as you go across a period, we're observing an increase in Z effective. Which means as you go across a period, you would expect to observe what kind of trend in first ionization energy? What? Increase. But you think there might be some exceptions to this ionization energy trend? Here's one. And it's the first one in the periodic system. Beryllium, which is larger than boron. This is more difficult to ionize. This one is larger, but still more difficult to ionize. Well, what do we know about the configurations for these atoms? Beryllium, 1s2, 2s2. Boron, 1s2, 2s2, 2p1. It's the first atom in the periodic system which has got an electron labeled p instead of s. And we already reminded ourselves, you got to get all the way to scandium before you got an atom that's got an electron labeled b. Because these are labels. SPD. I mean, there's a history to why S and P and D and F were used as opposed to just somebody plucking an alphabet number out of a lottery machine. I don't care about that history. Now, BE. B. I'm only paying attention to valence configs because we're talking about ionization energy number 1. Okay? Now then, this radial probability function will correspond to, or can correspond to, I should say, boron, but not beryllium. Because beryllium hadn't got any p electrons. Okay? Boron's got both. If this radial probability graph is correct, and studies corroborate that it is correct, if this is for boron, which of these valence electrons for boron, 2p or 2s, accounts for the size of boron? If this picture's correct. Which one? You're standing in this nucleus of boron. You're looking toward its exterior surface. Which electron or electrons do you see furthest from the nucleus? 2s! So which of these valence electrons is defining the size or accounting for the size of a boron atom? 2p or 2s? 2s. Now let's talk about ionizing boron. Based on MPD, when you ionize boron, which electron would you expect to remove? 2s or 2p? Based on MPD.
2s.
Which one would you expect to remove? 2s. Hell, it's got a bigger MPD. It's further from the nucleus. Well, let's take a look at this configuration for boron. 2s1, 2s2, 2p1. If I in fact take away a 2s electron from boron, when I turn boron into B single plus, by losing an electron, minus electron, that's what this means. If I take away a 2s electron, then I got a configuration 2s1, 2p1. I would have two half-filled valence orbitals. What property would B single plus now exhibit? Also exhibited by B, but not exhibited by BE. What property? Property you learned about in 2045. What property does this atom have that this atom doesn't have? What property is exhibited by any atom that's got a half-filled, at least one half-filled valence orbital? I'm listening. What is this property? Yop it out! It's called paramagnetic character. Yeah. You heard about that, haven't you? Paramagnetic character. A boron atom is paramagnetic. A beryllium atom is not. It has no half-filled orbitals. So I state to you, if boron loses a 2s electron, which you could expect from MPD, when boron converts to B single plus, I'd have a configuration 2s1, 2p1. I'd now have a species which would be more or less twice as paramagnetic as the parent atom, because now I got two half-filled orbitals instead of one. Okay? Nothing fancy about this. You did this in 2045. Now let's put it to use. Now let's talk about facts. Because B single plus, this thing, is not paramagnetic. It's diamagnetic. Well, that's screaming at me. When I take away this electron from boron to turn it into boron single plus, which electron am I losing? This one. How the hell can that be? This thing has got an MPD that's shorter than 2s. How can I preferentially take away this thing instead of one of these, since these are closer to the nucleus, MPD-wise? What's going on here? Furthermore, do you realize if I take away one of these 2s electrons, like if I take away one of these electrons here, I'm getting back a pairing energy. Did you hear about that in 2045? What's pairing energy? What do you think it means? Pairing energy. Why is it when you add electrons to equal energy orbitals, like a 2p sublevel? There's a line diagram for a 2p sublevel. You did this in 2045. We're now imagining to develop the configurations for atoms which have got 2p electrons in the ground state. Boron is the first one. It's only got 1p electron. Now here's carbon. It's got two valence 2p electrons, right? Well, right. Since I read left to right, I'm going to put my first electron in here. And the convention is to show the electron spinning up. I mean, that's not true, but it's just a convention. Because when we draw pictures of electrons, which is utterly impossible, to represent in some fashion their spin, we use this or this. But we do know that when we have a full orbital, it has no paramagnetic character. It's in fact diamagnetic. That tells us that when we have two electrons in the same orbital, are they ever spinning in the same direction? No, they're spinning in opposite directions. So here comes electron number 2. We're going to make a carbon atom. We've got to have two valence p electrons. Electron number 2, is it here or is it here? Did you ever hear about maximum multiplicity? This funny term in 2045? What the hell is maximum multiplicity? Why would you ever get this configuration before you get this configuration? Because if you get this configuration, as opposed to each of two p orbitals being singly occupied, you got to pay a pairing energy, because now you got to put two electrons in the same orbital, and these things are as close to each other as they can possibly be when they are in the same orbital, so they will repel each other to the maximum extent when they're in the same orbital. You don't get this. Costs too much energy. You get this. So back to this. If I turn boron into B plus and create a 2s1, 2p1 configuration, I'm getting back a pairing energy. That's energetically favorable. And I'm taking away an electron with a shorter MPD. So far, we have paid attention to properties of borons, valence electrons, which say the damn thing ought to become 2s1, 2p1 when it's ionized, but it ain't doing that. It becomes this. Why is that? You see this part of this graph? I'm shading it in. You recognize the part of this graph, which I just shaded in, is part and parcel of the 2s radial probability. The theoretical folks came up with a name for this. It's called the penetration region. And it accounts for why, independent of MPD, independent of this pairing energy, when you ionize boron and turn it into B single plus, you don't touch a 2s electron. You take away a 2p electron, because these 2s electrons have a much better penetrating ability than the 2p electron. These 2s electrons can penetrate more effectively through the 1s2 core than the 2p electron. That's what this penetration region is all about. That means on a time average basis, here's the real fun of electron behavior. On a time average basis, not only are 2s electrons for boron further from the nucleus, this MPD is bigger than 2p. On a time average basis, they're also closer. How about that? Because they got this greater penetration region, penetrating ability. These mysterious electrons with that damn dirty, nasty wave-like character. They do stuff which is very difficult for us to be able to understand in our minds. But if you always think of an electron as a dot, a particle, you're sunk. Because it ain't this electron, it ain't this dot, it ain't just this particle. It's this wave thing, which is at one time, one instant, at many places, in fact, an infinite number of places in space. How about that? We'll pick it up from this point tomorrow.